For the next topic we're looking at is filters. So filters, like if I made a filter for a water supply or something like that, it's able to remove certain sized particles while letting other sized particles flow through. So if I made a filter for a water supply that filtered out muck or sand or dirt or anything like that, it lets the water flow through because the water is small particles. The larger particles aren't able to flow through because they get caught by the filter or blocked. So in an electronic circuit, a filter performs a similar function, but instead of filtering out particulates, it's filtering out signals of different frequencies. Okay, so they're called a frequency selective circuit or selective network. So it selects or allows a certain range of frequencies through while blocking another range of frequencies. Okay. So before we get started, we're going to be looking at, in this topic, really 5 different types of filters. So we're going to have high pass filter, so high pass filter allows, as the name suggests, high frequencies to go through. Now, the best way that we can show this graphically is by graphing the frequency against its response or its amplitude. Okay, and so if we were to have an increasing frequency on the x-axis and the amplitude on the y-axis, we would see for a high-pass filter a response that looks something like this. Something that looks like this. Okay, so you can see the higher frequencies have a higher response or higher amplitude than the lower frequencies. Okay, a low-pass filter is a similar idea. It's just going to, instead of allowing the high frequencies to pass through, it's going to allow low frequencies to pass through. So it's going to look something like that. Okay, so allowing low frequencies to pass through while blocking the high frequencies. Now the 2 other types that we're looking at are band pass. A band pass is made up of both a high pass and a low pass filter, and the high pass part blocks these low frequencies and the low pass blocks these higher frequencies, but there's a gap in the middle, a band, that is allowed to pass through. So that is a band pass filter, and the 4th type of filter that we'll be looking at is something called a band stop. Okay, and as the name suggests, it will stop a band of frequencies at just one little range while allowing the others. So we have a low pass filter and a high pass filter, and in between there, so with a combination of those two, we're having a stopped band. Okay. Now there are a couple of different types of band stop filters. So there are general band stop filters which stop a certain range, but there is another type that we call a notch filter, and that stops a very, very narrow band at a very specific frequency. Okay. We'll be discussing and exploring these 4 different types of filters. Now, on top of that, we have what we call passive and active filters. So a passive filter is only made using passive components, so components that don't require an external power supply in order for it to operate. So effectively they're resistors, capacitors, and sometimes inductors. Okay? So each of those 3 components, they're what we call passive components. They don't require a power supply. An active filter is actually made up of a passive filter but using an amplifier. Okay? And there's 2 different ways that we can use the passive filters in the amplifier to make a active filter. So the active component of that is the actual amplifier circuit, which you'll remember we actually need a power supply as well as an input signal in order to make that amplifier work. Okay, so an active filter also needs an input signal and some power source, so you need some sort of power supply as well. And so the benefits of a passive filter is that they're really small. You only need a handful of components to make them work. You don't need external power supplies, and so it's cheap, it's compact, relatively easy to implement. The downside is that these can only attenuate, so they can only make a signal a bit smaller. We can't actually have a large, we can't make it larger, we can't amplify the signal as well. And it gets difficult to control things like the impedance and if we're making things like multiple stages, so like for example a band pass filter, it makes it difficult to be able to control these the frequencies that we get this sort of cut-off action here. Okay, so we'll talk a little bit more about that when we get to it. An active filter needs a power supply, so there's some extra complexity with that. It also needs an amplifier chip, so that there's some extra expense, and it makes it a little bit bigger, so bulky. And but the benefit is you can have an output that is actually bigger than the input. So if I can have some gain as well as my frequency selective control, and also I can control the input impedance, meaning I can have a very big signal on the input and still be able to filter it, whereas I wouldn't necessarily be able to do that with a passive filter because it would draw too much current and it wouldn't work properly. And I can also, if I'm making a filter that is like a band pass or a band stop, I can make these independent of each other. So rather than, we'll talk about how they interplay between when we have multiple filters with each other and how the problems that occur with that. We'll talk about that later. But basically, if I want to make a circuit that I can control just this lower cutoff frequency here or just this high cutoff frequency, I can do that with an active filter. It's quite difficult to do with a passive filter. Okay, so why do some circuits respond differently to different frequencies? So that's what we're going to be getting into. The first thing we're going to be looking at is passive filters. But in order to actually understand how a passive filter works, we need to understand what this circuit does. What's the name of this circuit? Anyone remember? Voltage dividers. Well done. Okay, so this is a voltage divider. And if I made R1 equal to R2, what can we expect the output voltage to be compared to the input voltage? It's going to be a half, isn't it? Okay. So the way to think about it is the resistance here as a fraction of the whole resistance is going to be equal to this voltage as a fraction of the input voltage. Okay. So a way we can think about it is like that. Okay, so that's just another way we can look at the voltage divider formula. So we're just looking really at the ratio of the voltages is equal to the ratio of this resistance to the total resistance. Okay, and if I were to increase R2, what does that do to V out? Does it make it get higher or lower? It goes higher, doesn't it? Okay, so increasing R2 gives an increasing V out. Okay, so it's important to remember if this resistance here increases, then this voltage will also increase with it. What if I increase R1? Increasing R1, what does increasing R1 do? It pushes this voltage down, doesn't it? Okay, and so it's a decrease. Okay, right, so if I had an input signal here that was a sinusoid like that, and it was, let's say, it was 1 volt peak to peak, and I adjusted these in such a way that they're equal, then I would have a 0.5 volt peak to peak. So it works for all signals or all voltages. So if I have a sinusoidal on this one, I still get the same sinusoidal on this one, but it's going to have some fraction of this voltage. Okay, so and if I were to increase R2, then that's going to increase this voltage. If I were to increase R1, that's going to decrease this voltage. Okay? So if I want to be able to control the output voltage, I can adjust these, or if I can control these resistances, I can control this output voltage. Okay? The key thing with a filter though is that we're going to be looking at components that they behave a bit like a resistance. They have something called reactance, and that reactance is still an opposition to current flow. Okay, so an opposition to current flow we've been calling it resistance up to now, but it's a little bit more detailed than that, because reactance has an opposition to current flow, but it is different at different frequencies. Okay, so we're going to look at the principle of reactance now. So keeping in mind, we're going to be using the voltage dividers, exploiting these voltage dividers idea with something that the resistance, or its opposition to current flow, is going to not just be determined by where I turn the knob on a thing, but also by the frequency that is that of our signal. Okay. Capacitors and inductors are two components that exhibit this thing called reactance, and it's an opposition to the current flow due to the capacitance or inductance at, you might say, it is frequency dependent. Okay? So I think we'll start with looking at a capacitor's reactance to begin with. Okay? Reactance has the symbol XC for capacitive and XL for inductive. Depending on whether it's a capacitor or an inductor, depends on how it's going to respond to that frequency. So for a capacitor, the reactance is quite low at very high frequencies and really quite high at low frequencies. For an inductor, it's actually the other way around. So an inductor has very low reactance, so low opposition to current flow at low frequencies, and very high reactance at high frequencies. At XL. Yep. XC and XL. Okay, so the unit is still in ohms. Okay. And for those of you going to do engineering, we also refer to something called impedance in a complex form, and instead of using I, like they do in maths, we use J to not be confused with current. Okay. But we won't be looking at that kind of behaviour in this course. Basically, you just need to be able to calculate the reactance at a given frequency for a given capacitance. Okay, so for a capacitor, XC equals 1 over, okay, so pi, 3.14, blah, blah, blah. F is equal to frequency. In hertz or cycles per second. The capacitance in farads. Okay? Now for the most part, well, 1 farad is a rather large capacitance. So like if I had a 1 farad capacitor, it'd be about the size of a Coke can or a bit bigger, right? So rather large, and probably only a couple of volts. The capacitors we use generally and will be experienced usually in microfarads at the largest, right down to picofarads. So a picofarad is 10 to the minus 12 farads, so it's pretty small numbers. So we're going to be, when we deal with these capacitors, we're going to be looking at really small numbers. So let's look at a couple of examples of how to calculate it. So, e.g., a 1 microfarad at 1 kilohertz. So this is a sort of typical kind of problem we might experience or might face. What is the capacitive reactance of a 1 microfarad capacitor at 1 kilohertz? So let's put that in. Xc equals 1 over 2 times pi, 3.14 times, and I'm going to use the scientific notation for these. 1 micro is by 10 to the minus 6 times 1. I'll have to use C first, so actually let's do frequency. It's in order, it doesn't matter what order you do it in. 2 times pi times the frequency, so 1 kilohertz is times 10 to the 3 times 1 microfarad, 1 times 10 to the minus 6. Okay, so if I put that into my calculator, what I do with these is I actually evaluate this bottom bit first, so I type all that in, and then I press the x to the minus 1 button, which is there. And I get 159 ohms. Terrible ohms. Okay, so if I had a 1 microfarad capacitor with a signal of 1 kilohertz, it would behave nearly the same way as far as the opposition to current flow. It will behave exactly the same as if I had a 159 ohm resistor there instead. Okay, so it would stop the current in a similar sort of way. There are a few key differences, but for the most part, it's going to stop it in the same way as a 159 ohm resistor will. So I'd like you to try this one now. So what is Xc for a 10 nanofarad at 20 kilohertz? So we've got a 10 nanofarad capacitor. So I might put the scientific notation here for you. I'd like you to actually do this calculation along with me. Right. So we've got 10 by 10 to the minus 9. It's going to be 20 by 10. Okay. So if you want to put this into your scientific calculator, the EXP button does this whole thing there. So by 10 is the EXP. Or some of the other ones have by 10 to the x. Okay, so they're the buttons you need to use to do that. And in my calculator, I'm going to get Xc equals 796 ohms to the nearest ohm. Alrighty, so we can calculate the reactance for a given capacitor and given frequency by just substituting our F and our C into that formula. Likewise, let's find our frequency. Does a 22 nanofarad capacitor have a reactance of 1000 ohms? So what I can do here is I'm trying to find F. We know that Xc is 1000. We don't know F. We do know the capacitance, so it's 22 by 10 to the minus 9. So what I'll need to do is transpose this equation, but because we've got on the top on the left-hand side and on the bottom on the right-hand side, you can just swap them, okay? So I can just swap the positions of the knowns and the unknowns in this formula. Makes it kind of nice, it makes it really easy to substitute, to transpose. So to calculate the frequency, that we would have a reactance of 1K for a 22N, and it would be 7,234 hertz, or 7.2 kilohertz roughly. Okay, so quite often we can satisfy ourselves with really 2, maybe 3 significant figures. We don't need to go too nuts on the accuracy here, so I'm not even going to 0.1 of a hertz. That's mainly because our accuracy of our capacitors and our resistors isn't really that high. Okay, so we're sort of within 5% usually for our resistors, and capacitors can be quite bad. So electrolytics, 20% for some of them. Okay, some of the ceramics is usually pretty good. So like a 22N capacitor would probably be about 5%. Okay. So yeah, 2 significant figures is usually good enough. So we can calculate the frequency, or we can calculate the reactance, or if we like, we can calculate the capacitance as well. Okay. So I'll leave that up to an exercise for you to test a few different ones. Okay. All right. So we've shown that capacitance has a reactance and it responds differently to different frequencies. So if I were to calculate the reactance of a 22N capacitor at a whole bunch of different frequencies, what we would see is that it would follow it wouldn't be the same amount each time. It would be changing as we go along. At 7.2 kilohertz, this capacitor has a reactance of 1K, but at 72 kilohertz, X is going to be much less, and it's 100 ohms. Okay, so you can see that the reactance here is 1/10 of what it was when the frequency is 10 times bigger. Okay, that kind of makes sense, doesn't it? Right? So there's sort of an inverse relationship between the reactance and the frequency. And so if I were to drop that frequency, increase that frequency again, we're going to decrease that resistance. All right. So now, how do we put that into practice? What we need to do is putting one of our components in our voltage divider, we make a capacitor. So if I had my voltage divider like that, then this is going to be having a frequency, it's going to have some reactance. So it's going to behave just like a resistor that is going to be changing based on the frequency. And that's going to affect the output voltage. Likewise, if I had a circuit like this, okay, it's going to have a similar effect, but just in the opposite sense, because remembering what we were talking about with the capacitance, as I increase this frequency, the reactance of this got smaller and smaller and smaller. So in this circuit, and to have the same effect as having a resistor here, that I'm decreasing its value. And so if I increase the frequency, I'm going to decrease this resistance, which will increase this output voltage. So at high frequencies, the output is going to be higher than at low frequencies. So this one is going to have a response that looks like this. So at high frequencies, we've got a higher output. At low frequencies, this resistance here, or the reactance of this, is very large, and so it pushes this output voltage down. And so at low frequencies, we've got very low response, and so that gives us this response. Now remember the diagrams we had before. This is frequency, and this is amplitude. What do we call this type of filter response? High pass, wasn't it? Okay. The high frequencies have a high response. Okay. So this is equal to, well, this one here is a high pass filter. Okay. Let's look at this one. It's just going to be the similar idea, but we're not changing this resistance. We're really changing the reactance, or kind of the resistance of this thing. And so at low frequencies, that resistance there is going to be quite large, and so this output is going to be large. At high frequencies, this is very small, and so the output is going to be small. And so if we were to plot the graph like that, low frequencies is very high, high frequencies is quite low, and so you get that, and that is what we call a low pass filter. Okay, so just to wrap it up, capacitors, just one component. Inductors also have this property called reactance, where they have an opposition to current flow that's determined by their capacitance and by how much energy they can store, because they are energy storage devices. So their capacitance for a capacitor, or their inductance, and the frequency. So the frequency of the signal that is, or the voltage across it, is what's going to be determining the reactance of it. And for a capacitor, high frequencies have a low reactance. And if we make a voltage divider using one of these components, we get a filter. Okay? And the filter has a different response to different frequencies. So a low pass filter has a good response at low frequencies, so the output is basically what the input is. And at high frequencies, it's very highly attenuated. So the output amplitude at high frequencies will be very low. Likewise, a high pass filter has, at low frequencies, the output is quite attenuated, and at higher frequencies, the output is allowed to pass through. Okay? And that's related to how our capacitors are placed in the circuit. So you'll notice that the similarities between the two voltage dividers that we've made, the two filters, are we've still got one resistor and one capacitor, but they're just in opposite positions. Okay?